Right, this is the fourth video in the Exp and Log section on modeling with Exp and Log, with exponentials and logarithmic functions. Just a little bit about modeling in general, I think, to set this in context. Why do we do this? Well, you will, if we've got a relationship between two variables that we're interested in, then really the model is a simplified form of that relationship. There may be all sorts of parameters involved if we're looking at the relationship between two variables. What we're trying to do is simplify it right down to give us an equation, a relationship that we then can use for predictive purposes. Now, it's a model, so it's not necessarily going to give us totally accurate predictions, but it's going to give us predictions that we can use. So that's basically the idea. It's to simplify a complex relationship to provide a mechanism for predicting. Now, there are different sorts of models. We can assume we can form a model which is, say, linear between two variables, just a simple straight line relationship. So that's what we've got here, y equals at plus b. I've used t here as the independent variable because very often these problems are time-based, in which we always use t for the letter there. They're not necessarily all time-based. It could be other things, but time is a pretty recurrent theme, and y is just a general variable which could relate to the value of a financial investment or the population of rabbits in a colony or all sorts of things. So y and t are the variables that we're interested in modeling. A and b will be unknowns, and this relationship won't be useful until we can actually find out what A and B are. So we have to resolve for those. Quadratic models we have, something of this form. Again, here A, B, and C are unknowns. These tend to crop up quite a bit. Very often we're looking at inverse quadratics where the coefficient of A is negative, but not always, but that does seem to be the most common type. And then we've got our exponential models, which look like this. A equals e to the power of kt. So this is a sort of a fairly straightforward exponential model, and in this case, if k is positive, then we see the graph rising up rapidly. If k is negative, k is always assumed to be a positive number, by the way, but if it's minus k t, then it will be an exponential decay. So that might reflect, say, the value of a car over time as it depreciates, something like that. The model might not be quite of that form. For instance, we may see not Euler's number e here, but some other number, might be an integer, 2, might be anything really, but very often there'll be a whole number in there. And then rather than kt, there might be something more complicated as the exponent there, possibly quadratic. But of course, a function which gets too complicated isn't going to be useful for what we want, which is, it won't be a model anymore if it becomes too complicated. Okay, so essentially what we need to do is identify what model we're using, and very often the question that we're asked to do, if it's a problem in an exam, then it will probably either state explicitly or imply what the model is going to be, which of these or others, in fact, it might be. Then we have to resolve for these unknowns. A and B, A and B and C, or K, and using the boundary conditions. Now, boundary conditions are a pair of values of y and t in this case, that if we substitute them into the equation, then it's going to help us to actually resolve for the unknowns. Initial conditions are a special form of boundary condition, basically where t equals 0, tends to relate to time-based problems. Okay, and then once we've got a fully resolved equation, and then we can use that in order to make predictions of y from t, or also predictions of t from y. Okay, so that's the basic idea. Just another couple of things worth saying is that we'll come on in a later section to the idea of log graphs, and that's just where, if this is our relationship, then very often it's useful, if we want to represent it graphically, certainly, if we take the log of both sides of the equation, we get something like this. And when in looking at this, we can see this looks like a straight line. Y equals mx. This is the gradient times your independent variable, and that is the intercept on the y-axis. So we can actually turn our exponential model into a linear model, which can be useful. We come to that in another video. The differential equations also are a form of modeling. And in this particular case, we would have to use calculus in order to find an expression of y in terms of t, and then resolve the unknowns that come out of that process. So that is a kind of the sort of general idea of modeling and where exponential models fit into that scheme of things. So we'll have a look at a couple of examples. Just use that. Okay, so here's one. The total number of views V of a viral video clip that is released on the internet is given by the formula V equals 150 times 2 to the power of D. So what we notice about this, first of all, it hasn't got any unknowns in it. It's already fully resolved. So we're sort of skipping that stage, but I think we can see that when D equals 0, then after 0 days, then the number of views is equal to 150 times 2 to the power of 0 is 150. So when it's released we're already with 150 views have happened, at the point it's released. Okay, so how many days does it take for the video to reach 1 million views? It might also say, of course, that here we're not using Euler's number. We've got a value of 2 here, but nonetheless, it's still an exponential model. How many days does it take for the video to reach 1 million views? So we're basically solving this equation. The number of views is equal to 150 times 2 to the power of D. Okay, so just dividing through by 150, we get 2 to the power of D equals this. And then in order to get this D from the argument into the subject of this equation, now we need to take the log of both sides. We take log base 2. Then we've got D equals log base 2 of 2000 minus log base 2 of 3. It's just applying your log rules, and that gives us D equals 9.38, etc. So that's how many days it takes for the video to reach 1 million views. Okay. Explain why this model will eventually break down. Well, it's a model, of course, and one thing about models is that they do tend to kind of work quite well within a particular range of values, and then outside that range, they become less and less useful and more inaccurate. Why would it break down? Well, eventually, everybody's seen it. So people are, not going to keep viewing it. People might look at it for a second or a third time, but eventually your marketplace, if you like, is going to be saturated. So it won't keep growing. But over a certain period of time, then it may well be a good model. Okay, so that's a relatively straightforward one. Let's have a look at this one. There's a little bit more to it. On 1st of January 1900, a sculpture was valued at 800, and when sold on 1st of January 1956, 6 years later, its value was 5,000. Okay, so we're given this model. V, the value, is equal to A times K to the power of T. The T is the time in years since this start point here, 1900. A and K are constants. Write down the value of A. Okay, so there we've got our equation. I mentioned that these are the boundary conditions, but of course the boundary conditions are not always given to you explicitly, T equals 0, V equals 80. Sometimes they're implicit from these statements, so you have to be able to pick those out of there. So in this case, we've got when T equals 0, V equals 80. We plug those values into the equation, then we're going to get 80 equals A times K to the power of 0, K to the power of 0 being 1, and therefore A is equal to 80. And then it says show that K equals 1.07, etc., to 5 decimal places. Well, we've got to the point where we say V equals 80 K to the power of T. So if we then take that equation and substitute T equals 56, V equals 5,000, which is what we've got from this statement, then when we rearrange that, we're going to get K to the power of 56 equals 62.5. And then if we take the 56th root of 62.5, that's something you do every day, but your calculator will handle that quite happily. That's going to give us you a K of 1.076, etc. So that is it. And therefore, we now know that our fully resolved equation is this: for V equals 80 times 1.07664 to the power of T. Right, so in part C, it says use the model to show that the value of the sculpture on 1st of January 2006 will be greater than £200,000. So essentially, we're just using our equation, which is already explicit in V. Substitute T in. V equals 80 times 1.07664 to the power of 106. Pop that in the calculator, and that's going to give you this value, 200,707, which of course is greater than 200,000. So we've shown it's greater than 200,000. That's part 1, and then C part 2. Now this is quite typical. Find the year in which the value of the sculpture will first exceed 800,000. So we have to put that into an equation. So this is the value, the function of T that gives you the value, and that's got to be greater than 800,000. Divide through by 80, and we're going to get 1.07664 to the power of T is greater than 10,000. Now, in order to move this T from the argument of a function, this is an exponential function here, so from that into the subject of the equation, then we're going to take log of both sides. In this case, it's a log of, and this is the base of the log, which is a bit strange, but that calculator will handle that quite happily. So T equals that, which is 124.687, etc. So therefore, the answer is 124 years later in the year 2024. Okay, so this is quite a typical form of problem where we have our problem, we have to apply our boundary conditions to get the resolved equation. Then we use the equation first of all to find to find a value of v for a given value of t, which is nice and straightforward because v is the subject of the equation. But then we're asked to find the value of t for a value of v, so we have to go apply our log rules in order to actually solve that equation. And in this case, they're basically inequalities that we're working with, but the same principles will apply. Okay, so that basically is what we do with modeling Exp and Log. So hopefully you've gleaned something from that, and I'll see you in the next video.